All right, let's talk about a really cool networking trick that lets you get way more speed and reliability out of the connections you already have. It's called Ether Channel, and trust me, by the end of this, you'll know exactly how to supercharge your network links. So let's jump right in.
So, before we can appreciate just how clever Ether Channel is, we first have to understand the problem it was built to solve. And it all kicks off with a super common and, honestly, a pretty frustrating issue in network design.
Okay, picture this. You're managing a network, and you desperately need more bandwidth between two of your most important switches. Your first thought, and it's a logical one, is to just plug in another cable, right? I mean, double the cables should mean double the speed, plus you get a backup link. Simple. But if you've ever actually tried that, you know the network has other ideas. So what's really going on here?
Well, what's going on is a protocol called spanning tree, or STP, jumps into action. Now, STP has one very important job: to stop catastrophic network meltdowns called switching loops. And the way it does that is by sniffing out any redundant paths, like that second cable we just plugged in, and immediately blocking one of them. It's an absolutely essential safety feature, but it means our extra cables are just sitting there doing nothing.
And that leaves us in a bit of a pickle, doesn't it? On one hand, we're safe from those network-killing loops, which is obviously great, but on the other hand, we're right back where we started, stuck with the speed of just a single link. We've got all this extra hardware ready to go, but the network's own safety rules won't let us use it. There's got to be a better way.
And you know what? There is. This is exactly where Ether Channel comes into the picture. It's not about trying to fight spanning tree, it's about being smarter than spanning tree.
So what is this thing? Well, to put it simply, Ether Channel is what we call link aggregation. It lets you take a whole bunch of separate physical cables and basically wrap them up in a trench code, tricking the network into seeing them as one single, massive logical connection. It's like creating a supergroup for your network cables.
And here is the magic trick, as you can see right here in this diagram. By bundling, let's say, 4 physical links into one logical port channel, spanning tree doesn't see 4 different paths anymore. Nope, it just sees one giant data highway. And since there's only one logical path, there's nothing for STP to block. All of your links stay up, all of their bandwidth gets combined, and just like that, problem solved.
Okay, so now that we get the big idea, let's dig into the awesome benefits this gives us and, just as important, the rules you absolutely have to follow to make it work right.
The advantages here are frankly fantastic. First, and most obviously, you get a huge boost in bandwidth. You bond 2 1 gig links, you get a 2 gig logical link. Easy. Second, traffic gets spread out, or load balanced, across all the cables in that bundle automatically. Third, you get incredible redundancy. If one of the physical cables gets unplugged or fails, traffic just shifts over to the others seamlessly. The network doesn't even flinch. And to top it all off, it's cheap, you're using existing ports, and it makes your life easier because you only have to configure one logical interface instead of 4 or 5 or 8 physical ones.
Now, to get all that goodness, you have to play by a few golden rules. As you can see here, every single port you put into an Ether Channel bundle has to be a perfect match. You can't mix and match, you can't throw a fast Ethernet port in with a gigabit port. They all have to have the exact same speed, the same duplex settings, and the same VLAN configuration. The one word to remember here is consistency. Everything has to be identical.
Okay, so we know the rules of the game, but how do two switches actually, agree to form one of these channels? They don't just do it on their own. They have to talk to each other. They have to negotiate. And for that little chat, we have 2 main protocols they can use.
And this negotiation part is super important. It's like a handshake that lets the switches double-check that all the settings match on both ends before they build the channel. It's a great safety check to prevent problems. The 2 languages they can speak for this are called PAGP and LACP.
So let's put them side by side. On the left, you've got PAGP, which stands for Port Aggregation Protocol. The key thing to know about this one is that it's Cisco proprietary. It only works if you have Cisco switches on both ends of the wire. On the right, we have LACP, the Link Aggregation Control Protocol. This one is the open industry standard, which is huge because it means you can create an Ether channel between a Cisco switch and a Dell switch or a Juniper switch or pretty much anything else. Now, look at their modes. They're basically the same idea with different names. PAGAGP uses desirable to start the conversation and auto to listen. LACP uses active to start and passive to listen.
So, how does that negotiation actually play out? Well, for PAGP, at least one side has to be set to desirable to kick things off. Think of it like asking someone to dance.
If one person asks, desirable, and the other is willing, auto, you get a dance. If both are eager and ask, desirable and desirable, you also get a dance. But if both sides are set to auto, well, they just stand there passively waiting for the other person to make a move. And nothing ever happens. No channel for you.
And guess what? The logic for LACP is exactly the same, just with those different mode names. Active is the one who initiates, passive is the one who listens. So active plus active works great. Active plus passive also works perfectly. But if both sides are set to passive, yep, you guessed it, they'll both wait around forever. The rule is simple. Somebody's got to be willing to start the conversation.
All right, that's enough theory. Let's get our hands dirty and see how you actually build one of these in the real world. It's way simpler than you might think.
It really just boils down to these 3 simple steps. First, you tell the switch which physical ports you want to bundle up. Second, you give the command to create the channel group, and you tell it which mode to use. We'll use LACP active for our example. And third, and this is the important part, you do all of your real configuration, like making it a trunk link on the new logical port channel interface that just got created. And here it is. This is what it looks like on the command line. First, you see interface range fast Ethernet 04/1-2. That's us selecting our 2 ports. Then comes the magic command, channel group 1 mode active. The switch immediately tells us it's creating the logical interface, port channel 1. And then we just go into that new interface and configure it just like any other port. In this case, we're making it a trunk. It really is that clean and simple.
And this quote right here really hammers home one of the best parts of this whole thing. Once that channel is built, you forget about the individual physical ports. You just work with the one port channel interface. If you need to change a setting, you do it in one place, and it automatically pushes that change down to all the physical ports in the bundle. This is a massive win for keeping your configurations consistent and saving you from silly mistakes.
So there you have it, Ether Channel. It's a brilliant, elegant way to combine bandwidth, add rock-solid redundancy, and make your life a whole lot easier, all with the hardware you probably already own. You now know how to build bigger, faster, and much more resilient networks. So the only question left is, what part of your network are you going to supercharge first?